Okay, so what we're going to do now is we're going to do a very simple case, the simplest case we can. So we've got the daisy. We've got the linear Schrodinger's equation. So we want to consider the delta function, the case where u is a delta function. Okay, so our u is equal to u naught times the delta function. So the delta function potential can be thought of as this limiting case here. So we can have a well, remember that going up corresponds to trapping. So we have one that goes from minus epsilon to epsilon, and we want the area to be equal to 1. So then we assume that the height here is 1 over 2 epsilon. So if we take the limit as epsilon goes to 0 of this function here, which is equal to 0 if x is not an element of minus epsilon to epsilon, gosh, my element, and is equal to 1 over 2 epsilon if x is between those. Then we end up with a delta function taking that limit. So, and you know that the property of the delta function is that the integral from minus infinity to infinity of w of x times delta of x is, and it selects the value of the function at a point. Okay, it's quite complicated, sort of strange function, but it's super important. And it arises in lots of applications, even though it's not really a function, is it? It's a generalized function. Okay, so we're going to solve for this case of a delta function, which we're allowed to have different depths. So u naught means it's deeper in a sense, it's a stronger delta function. Okay, so it'll be more strongly trapping. And we're going to look at this case here, and the case when lambda is greater than 0 and lambda is less than 0 separately. Well, we're going to start out with the case when lambda is greater than 0. So outside the region here, outside the region, where, well, in fact, anywhere but x equals 0, then we just got the second derivative of u is equal to, okay, so for x not equal to 0, we've got the second derivative of w is equal to minus lambda w. Okay, so that has solution if lambda is greater than 0, or if lambda is less than 0, so lambda is equal to minus k squared, that's going to have solution w is equal to a e to the minus k, e to the kx plus b e to the minus kx. Okay, so we can solve the equation really simply and get these two different solutions depending on the sign of lambda. Alright, if lambda is greater than 0, then we're going to get w is a e to the I kx plus b e to the minus I kx. Okay, I'm going to stop there and then we'll carry on and try and solve it for these different cases when lambda is less than 0 and when lambda is greater than 0.